Hello, it's Scott Manley here, and today I have for you an answer to a deep space question, a deeper answer to a deep space question. These are questions that are asked by supporters over at my Patreon, people that have signed up to support my random blitherings on the internet and occasionally ask questions, and I decided that I should probably do some research to actually answer these and give them their money's worth. So this question comes from Russell Nielsen, who said, assuming that there will be mining and smelting operations on the moon, how would you launch the resulting products into lunar or even Earth orbit? Spin launch, chemical rockets, electromagnetic angled ramp, or other? And I'm going to say we're going to manage to get all of those categories covered. But let's start by talking about what the moon is actually made of. What could you get from the moon and what could you use? Now, the moon may not have an atmosphere. You might be surprised to know, however, that the majority of the moon is made of oxygen. It's just oxygen that is bound up into various mineral oxides. Silicon dioxide is one of the most common. Aluminium oxide is pretty common too. There's calcium oxide, iron oxide, magnesium oxide, titanium oxide, sodium oxide. Yeah, there's also a little bit of potassium and stuff like this. But notably, one thing which is pretty rare on the moon is something called dihydrogen monoxide, or what most people call water. Now, while it does exist around the moon, it's largely been baked out of the surface by those long, hot days because there's not a lot of shade on the moon. But it is found in some places, such as permanently shadowed polar craters. A Lunar Prospector mission, it actually found the signature of hydrogen near the poles with its neutron spectrometer, and the L-Cross mission, it slammed like a Centaur upper stage into a permanently shadowed crater on the moon, and then a second spacecraft on the way in flew through the like debris plume, and it found about 5% water in that ejecta plume. And then there's also things like helium-3, which in science fiction words is of course needed for nuclear fusion, but it does actually get embedded in the lunar crust from like solar wind. And yeah, okay, it could be used hypothetically for some forms of nuclear fusion, which would be neutron or aneutronic fusion. But I can't say that in the short term it's a mineral or material that's going to necessarily make a difference. And also, I'm not even sure that in the long term it's going to make a difference. The moon isn't really rich in precious metals or anything like that, but whatever, for spaceflight, the resources on the moon have the massive advantage of being way outside Earth's gravity well. In theory, the energy costs of delivering materials from the moon to cislunar space are about 5% of the costs of delivering the same materials from Earth. The kind of things that I can see launched from the moon will be structural materials in the form of aluminium, titanium, but we've also seen things like Blue Origin developing solar cells that could be manufactured from lunar resources. So, how do we launch from the moon when we want to use lunar materials to be the cornerstone of our space industry? Well, the orbital, the escape velocity from the moon is about 2.5 kilometers per second, and the orbital velocity is about 1.7 kilometers per second. These are both massively lower than the Earth, which is about 7.8 kilometers per second, I think, to get into low Earth orbit, and 11 something or other to get out to the moon. The moon's going to be definitely a lot easier on that. But the hard part about the moon using traditional rockets is the moon is very poor in volatiles. That is anything which tends to vaporize when it's heated up. It's stuff that will tend to evaporate away. And the stuff that we use to make rocket fuel tends to be volatiles. Now, to be clear, we have lots of the oxidizer side of the equation, right? When we are making these aluminium, silicon, whatever, we are taking the oxygen out of that, and we probably will have lots of oxygen left. So you can have as much oxygen as you like, but the stuff that you would burn with oxygen, that is vanishingly rare, right? Now, we do know, yes, that there is some water at the poles. We don't know just how much is there, whether it's enough to sustain industry for a long term, a short term, or just one launch. This is the kind of mission, finding about this stuff would be the kind of mission that like a Viper would have been doing if it wasn't cancelled. But yeah, it is on a small scale, it's absolutely viable that we could extract lunar water from wherever and then electrolytically split that into hydrogen and oxygen, and then you would have rocket fuel, right? Hydrogen and oxygen. And that has an existing heritage. You could take a engine from the Earth and create hydrogen and oxygen on the moon and run your rocket engine on it. Problem solved, right? But if hydrogen is rare, what you might want to do is, say, combine it with carbon to make a hydrocarbon. Now, that won't be as good specific impulse, but you'll have a lot more fuel for your very limited supply of hydrogen. Now, classic hydrocarbons are things like methane, right? A carbon with 4 hydrogens around the outside. Yeah, you could definitely do better in terms of, your limited supply of hydrogen, except that carbon is even rarer than hydrogen. And I think this is because carbon forms carbon dioxide and carbon monoxide, and both of those are even more volatile than water. So those carbon-bearing materials, those disappear faster than water. We also don't form things like carbonates on the moon because it doesn't have like a water cycle or anything. But, but if you wanted an alternate form of rocket fuel to make the most of that very limited amount of hydrogen you could have, well, if you look at the periodic table, right, carbon is useful for hydrocarbons because it has 4 chemical bonds, right, around it, roughly speaking. If you look below on the periodic table, there's another element which has 4 bonds, and that is silicon. You can actually make a lot of silicon analogs to carbon by just swapping out the carbon. So there is something called silane, where you have a silicon atom and then 4 hydrogens around the outside. And this will absolutely burn like a rocket fuel. And silicon is everywhere on the moon. So you could make you could use this to augment your limited supply of hydrogen, make a silane-based rocket. And that's great. One of the nice things about silane is that it's actually hypergolic with oxygen at reasonable temperatures. It will spontaneously combust, so you could solve a lot of your combustion and ignition problems. Now, the downside is that when you burn silicon with oxygen, you get silicon oxide, silicon dioxide. You're producing sand in your rocket exhaust. Now, it's vaporized initially, but as it goes downstream, if it cools down, you can get sand, quartz deposits forming on critical stuff, or you could just be sandblasting stuff downstream. But still, silane-based rockets, totally a viable option if you're wanting to launch stuff off the moon using local materials. Another type of rocket could use aluminium and oxygen. Now, turns out, by the way, that most solid rocket motors that we launch rockets with, most of the energy, the burn, comes from perchlorates combusting with aluminium, because aluminium actually has a lot of energy in it when it burns. We don't think of aluminium as something as burned, but it totally will do that. So you can actually make a rocket motor with that. There's like ideas called a flash bulb rocket, where it's like just like very fine wires, and you blast through the oxygen. It burns very, very quick, and you get a quick thrust to put yourself into orbit. But there have been designs which use slurries of liquid oxygen and very fine-grained aluminium powder, and you burn that like a solid rocket motor, or you can even you can actually blow dust by having the oxygen flow through it as well. So this is totally a legit item which has been investigated, making rockets from aluminium and all liquid oxygen. Now there's some other option. Another option I've heard is a liquid metal alloy rocket. So there's potassium on the moon. It's not that common, but there's a decent amount of it. There's sodium. If you mix potassium and sodium together in the right ratios, you actually get an alloy which is liquid at reasonable temperatures. So you could use that as a fuel. Now you could also, if you want to get a little more energy, you could probably mix in some aluminium, find your exact perfect ratios, and then burn that with liquid oxygen. And then you would have 2 propellants that you can, in fact, burn. Again, this is something that you can look at. The potassium, by the way, comes in the Maria. These large lava, flat areas which were lava flows. The materials in it is called creep. It's like K for potassium and rare earth elements and phosphates. turns out that potassium is fairly radioactive, relatively speaking, and it forms a lot of heat. So potassium-rich regions of the moon would remain liquid longer, and you would get volcanic activity. Anyway, yeah, you could absolutely build a rocket engine using liquid metal alloys, and then you could actually control it by turning a valve on and off and maintaining the temperature. So that's another type of rocket engine you could build. And of course, if you've got oxygen, you could just have a cylinder, high pressure cylinder, heat, and let it out. Cold gas, you could heat it up if you want. There's a limit to how much you want to heat up oxygen, because if it gets too hot, it's going to attack things because it's an oxidizer, and you'd rather it oxidize a fuel rather than your engine. So now let's get away from the rocket engines and start talking about mass drivers. Now that's really a general name for a whole bunch of different technologies that will take a payload and accelerate it up to at least orbital velocity 1.7 kilometers per second, or 2.5. Now, to get an idea of how fast this is basically a space gun. And 1.7 kilometers per second orbital velocity on the moon is about 5,500 feet per second. And that's a strange number, but it's actually the number that a lot of firearms people talk. And I looked up, and the fastest bullet that I can find that can be fired from a somewhat conventional gun is a round called the .22 Irgen Splitten Laudenbomber. I think that's how you're supposed to say it, right? And even that was basically what they did, was they took a .378 Magnum case and charge and put a tiny .22 bullet, on it, mated that to a suitable breech and barrel, and that was able to fire at 4,500 feet per second. So even the fastest bullets that were built for firearms are slower than the orbital velocity from the moon. Anyway, you're probably not going to be using chemical propulsion to accelerate stuff inside barrels like guns on the moon, simply because, again, you don't have any fuels to go with your oxidizers. No, instead, we're probably going to be doing it with electromagnetic accelerators. So the classic mass driver was envisaged by Gerard O'Neill and his High Frontier, and it was a coil gun. And they actually built an example of this in the 1970s with MIT. So a coil gun essentially has a series of coils that get activated in sequence, and the changing magnetic field interacts with a projectile. It can either have like permanent magnets in it, or it can generate eddy currents and then push it or pull it depending upon the design. The one that they built in the 1970s accelerated at 30 G and shot the stuff out at, 40 meters per second. So if you just scale this up and make it longer, bigger and longer, you could eventually reach orbital velocity or even escape velocity. Now, how big, how powerful? That's a question you're asking. Well, turns out there's some very simple back of the envelope math that we can use to figure this out, right? So first of all, in terms of the amount of power required, it's simply kinetic energy. 2.5 kilometers per second is about 3.1 megajoules per kilogram. And that is about 75% of the energy per unit mass that you get in TNT. But yeah, that actually, if you think about it, then that means that the amount of fuel needed to accelerate 1 kilogram to this speed is generally going to be less than the mass of that object. By the way, yeah, 3.1 megajoules per kilogram, that's equivalent to about 6 Twinkies. Yes, 135 kilocalories. Of course, there are inefficiencies in the system. You might need more than 6 to feed them. And by the way, Twinkies aren't actually something that is found on the moon naturally. So I don't know why I went there. When I speak about energies. Look, okay, let's talk about the size of this. You can figure out the size of the gun by the amount of acceleration you want to give it. So you know the velocity it needs to get to. If you imagine it's accelerating in a linear rate, then the length of the barrel becomes, or the length of the acceleration section is 1/2 of the ultimate velocity squared divided by the acceleration. So for about 2.5 kilometers per second, that works out to 320 kilometers divided by the acceleration in g. So if you had a human being accelerated at 1 g on the moon, that would be 320 kilometers, right? If you maybe shrunk it down to 3.2 Gs, which is quite doable, you could sit in a seat, you could accelerate to lunar escape velocity in 100 kilometers. So that's roughly the size of the thing you're doing. But maybe you're not launching a human. Maybe you're just throwing chunks of rock up there. Well, let's accelerate it at 32 Gs. Then it'll only need to be 10 kilometers long. If you accelerate it at 320 Gs, that's only 1 kilometer. So you can see how you can very quickly make these things compact. The size of these structures are not that far off from things that we have on the Earth. If you look at CERN, if you look at the Large Hadron Collider, it's quite big compared to this. Granted, you know, it wasn't having to be built on a moon that was a long way away and had very limited infrastructure. But again, it starts to seem fairly doable. Now, powering this kind of thing, that would require a storage system which could charge up slowly using, say, solar panels or nuclear power, and then it would be able to rapidly release the necessary power in the time it took to accelerate the object. Now, batteries are great in terms of their energy density, the amount of power you can put in for a given size or a given mass. But the thing with mass drivers is that they need to release the power very, very quickly, and batteries don't tend to release as quickly. So you have to go with capacitors. Those are an option. They're a lot bigger than batteries, but they can release the power very, very quickly. Now, there's another option, which is superconducting coil storage, where you essentially have a big superconducting coil in, you know, cryogenics to keep it below its superconducting temperature. And if you put a magnetic field onto this, the electricity is flowing around, it's creating a magnetic field, and since it's superconducting, it doesn't go away. You've stored the electrical power in the form of a magnetic field. And then if you change the contacts to flow a different way, the power will then come out, the magnetic field collapses, and you get that energy out very, very quickly. So superconducting coil storage is better than capacitors in many ways, and that could absolutely be a viable way to store power for a mass driver on the moon. Again, we're not going into too much detail as to the exact mechanism by which these things are launched, whether, you know, it's a coil gun, a rail gun, or a linear motor or something like that. So anyway, another thing about this, by the way, is that if you're accelerating an object with magnetic fields, it needs to be able to interact with these electromagnetic fields. It wants to be a highly conductive substance, but maybe what you're throwing to space isn't going to be particularly conductive. So what you'll do is you'll wrap it in like a payload container and accelerate that. Or you could have the payload container basically be a bucket which you dump stuff into. The bucket gets accelerated down the line, and when it reaches a certain point, it starts decelerating, and the material inside it shoots off into space. So you could then slow the bucket down, recover some of that energy, by the way, to your energy storage, and then return it to the start of the launch track, getting ready to fire again. So that's another thing to consider, that you might have like a series of buckets that are just running and shooting stuff out into space. Anyway, spin launch, that was mentioned, and as ridiculous as spin launch is on the planet Earth, it starts to make a lot more sense when you're dealing with the lower velocities of the moon and the fact that the moon is a vacuum and you don't need a giant vacuum chamber. The nice thing about spin launch in this context is you don't really need a massive energy storage system in the same way, because you're putting the solar power into the spin rotation system, and it is basically storing all that power as kinetic energy. And now most of the energy is actually going into the arm because it's quite heavy, and you're spinning that up. You'll probably actually have two masses on here which get released at the appropriate moment and they shoot off. Now, the accelerations for a spin launch system are lower than they need to be on Earth. You could probably make it a bit lighter, a bit smaller, and since there's no, you know, since there's nothing around, you can really have your pick for where you shoot stuff. Now, after you've released your masses, you then do want to have a storage system to recover the energy back in. But yes, spin launch as a concept, it generates higher Gs than a linear accelerator, but it's more compact. It's something that you can fly down, you possibly put on a spacecraft and land on the moon and get going probably a little more quickly. Now, one other thing to realize is that these mechanisms by which you throw stuff off into space you are going to need to catch them somehow. You also need to think about what way you're throwing the objects. Now, if you throw it like straight towards the Earth, that may not be best. Generally, you're better to aim the stuff towards either the leading or the trailing Lagrange point, the L4 or the L5 point, partly because they'll actually have to climb uphill and they'll arrive with a little lower energy. And at that point, they're sort of somewhat stable. So it's a good place to actually set up your industry up there. But to get there, you might need small corrections to your orbit. And that's where these small thrusters, perhaps pressurized oxygen thrusters, could work. Another one, by the way, you could use is just have an arc jet. An arc jet which passes a lightning bolt through the oxygen and then shoots it out the back. Now, I don't think that would last very long because it'll tend to just destroy the rocket engine, but these are only needed for a very short amount of time to trim the velocity and put it in the right place so it can get caught by something else. Anyway, if the thought of building a 300-kilometer long linear launch system doesn't scare you, then there's a more efficient possibility for the moon. You could actually build a lunar space elevator using pretty much existing materials that are available today. So a space elevator, you probably know, is a cable that runs between the surface of a planet or a body and some point out in space. And typically there's a counterweight out there. And if you imagine the Earth is rotating, the counterweight gets held out and it holds it tight, and you can run stuff up and down this cable. Now, the moon is tidally locked to the Earth, so it doesn't quite work in the same way. What you have to do is have your cable come up from the lunar near side, pass through the Lagrange point, the L1 point, the point of gravitational balance between the Earth and the moon. And as you go over the other side, at some point you maybe go like another 35,000 kilometers, and you have your counterweight. So you're talking a cable which is maybe 80 to 100,000 kilometers long, depending upon the size, connects to the lunar near side, and you can run cable, spacecraft, cars, climbers up it. And it's actually slightly longer than an Earth-style space elevator, but because the mass of the moon, the gravitational forces are so weak, the gradients are so small, it's actually easier to build in many ways. The structural strength of the materials needed to build a lunar space elevator are a lot weaker, a lot less demanding than that is capable or is required for an Earth-based space elevator. Like, we could do this with existing polymers that you can buy off the shelf here. Things like Kevlar and Xylon absolutely work. You don't need to get your dislocation-free, perfect carbon nanotubes, which you would need for something on Earth. So, yeah, you could build a space elevator. Now, I looked at one particular example, said that, if you have near side surface of the moon and the Earth, you would go out, 85,000 kilometers from the moon. For every 1 kilogram of cable, you would need 1 ton of counterweight out here. Now, a 1 millimeter, square millimeter cross-section cable will carry about 5,800 newtons of tension, right, of load. If it's 85,000 kilometers long, that's 133 tons. So that would then, if you have 133 tons times 1,000, 133,000 tons, that's a small asteroid. It's not even that small an asteroid. It's like a Chelyabinsk, maybe a bit bigger than a Chelyabinsk-sized asteroid, to put that amount of load out there and balance it. The trick then is that you have to be able to capture the asteroid and put it in an appropriate orbit so you can lasso it. Also, incidentally, we've talked about the space elevator connecting from the point on the near side. You could absolutely have other connections that go to the lunar South Pole and stuff. And then, you have a robot, a climber, which can climb up this and drop the payloads, drop the materials into the appropriate orbit. This is something which is within our technological understanding right now. Now, it's not trivial. There's all sorts of problems to solve. For example, the best polymer that we have in terms of strength to weight ratio is Xylon, and that has issues with ultraviolet radiation. There was a whole scandal where bulletproof vests that were using this were breaking, were failing well before their lifetime because moisture and ultraviolet was causing them to break down. In deep space, you won't have the moisture, but you will have a lot of ultraviolet. So it's not entirely a solved problem, but we believe that it is well within humanity's technological grasp to build a lunar space elevator. And once you have a lunar space elevator, you can bring materials up, to whatever place you need, and then depending upon where you release it on your elevator, it can go into specific orbits. And if you build one on the other side, you can actually go way, way out and release an object at the right time, and it will basically get a free transfer to Mars if you make it big enough and long enough. So this is an exceptionally neat thing if we could ever build it. So yeah, Russell, I hope you found that interesting. I hope that all of you found this interesting, if a little bit rambly. And yeah, if you have questions like this that you think I can answer, again, go over, support me on Patreon, and I pick questions out of this list. It takes a while to sometimes find the good ones, but you could be getting your name checked here, and maybe you could be the one that gets me to talk about a sandstorm-powered rocket. I'm Scott Manley. Fly safe.